What principles govern the formation of molecules? What is chemistry's role in beer making? What do the new approaches in chemical synthesis hold in store for us? Less than 100 atoms exist in nature, and all the substances on our planet and in space are built from them. Generally, atoms combine among themselves to form several thousand different molecules. But some atoms can be found in nature in a pure state. One of the most striking examples of this is carbon. From an arrangement consisting wholly of carbon atoms, two different crystalline arrangements will yield two materials as dissimilar as the graphite of a pencil's lead and the diamond in a magnificent necklace. The liaisons that occur between atoms are the pillars of the world in which we live. The matter that makes up our universe is the result of ongoing transformation, known as chemical reactions. At every moment, both around and inside us, chemical elements and compounds come together and separate. Thanks to the work of several generations of chemists, light is at last being shed on the rules that orchestrate this perpetual ballet. They have discovered that the properties of chemical substances and the reactions they are subject to are explained by atomic architecture. Atoms are the elementary building blocks of matter. A little like our solar system, they consist of a central nucleus surrounded by even smaller particles called electrons. The nucleus is itself made up of two types of particle: protons that have a positive electrical charge and neutrons that have no electrical charge. As for electrons, they have a negative electrical charge. What keeps the electrons close to the nucleus is the attraction between the opposite electrical charges. If all atoms were identical, the universe would be made up of a single, absolutely homogeneous substance. This obviously is not the case. However, the number of basic chemical elements that exist in our universe is limited. Over the centuries, chemists discovered that everything in the universe was built from only 92 simple substances. These substances are called chemical elements. What differentiates chemical elements from laboratory elements is the number of protons found in their atomic nuclei, their atomic number. This number of protons, or atomic number, determines the relative weight of the different chemical elements. Thus, hydrogen, composed of atoms with only one proton, is the simplest and lightest of all chemical elements. Conversely, uranium, whose atom contains 92 protons, is the heaviest natural element. The atomic number of all the other natural chemical elements is situated somewhere between the two extremes. Atoms form the raw matter of the universe, but they are seldom found in a pure state. Most of the time, they combine among themselves to form chemical compounds. In a chemical compound, the atoms of one or several elements are attached to each other by very strong ties called chemical bonds. These assemblages of atoms, sometimes up to several thousand of them, are known as molecules. There are hundreds of thousands of molecules in nature. Life depends directly on their existence and the reactions they take part in. But how do molecules form? Molecular formation is the result of the positioning of the electrons in atoms. Indeed, electrons are not placed at random around the atomic nuclei. Quite the opposite. They are assembled in several consecutive layers. These layers of electrons could be compared to the rows of seats in a theater hall. Each layer contains a certain number of seats that can be occupied by electrons or left empty. However, like any theater hall, atoms seek to fill as many of these electronic seats as possible. If all their electronic seats are occupied, atoms acquire great stability. Such stability is, in a sense, the ultimate goal of all atoms. Few atoms ever reach that goal. For the most part, they begin by filling the electronic layers closest to their nuclei. But their outer electronic layer almost always has empty seats. For example, the outer electronic layer of the oxygen atom, which has 8 seats available, is only occupied by 6 electrons. So there are 2 unoccupied seats. The same applies to hydrogen atoms. Their 1 electronic layer is only occupied by 1 electron, whereas they need 2 to be stable. Because their last electronic layer is not full, oxygen and hydrogen atoms are unstable. However, they can easily become stable by pooling electrons. For example, if you mix hydrogen and oxygen and subject the mixture to a spark, the 2 elements combine to form water. In fact, every atom of oxygen will pool electrons with 2 other hydrogen atoms. The oxygen atom brings 1 electron to every atom of hydrogen. At the same time, the atom of oxygen receives an electron from every atom of hydrogen. The molecule of water thus formed is particularly stable, which explains the abundance of that compound on our planet. Today we know that it's this kind of cooperation between atoms that created matter and even made life possible. Chemists do not all work out of university labs. A great many of them work in industry where they develop high-quality products. Beer, for example, a sample of which you may be enjoying at this very moment, is the result of a series of complex chemical reactions. For you to be able to enjoy it as you do, a great many specialists had to be involved. Since time immemorial, one drink has charmed people and brought them together in great numbers: beer. We drink beer for its taste, the feeling of relaxation it provides, and even for its nutritional qualities. While beer making draws its techniques from methods as old as the hills, brewing has become a veritable industry today. Like many industries, brewing is based on a series of chemical reactions generated by natural products. The main ingredient is barley. Grains of barley consist primarily of starch, a chemical compound whose molecules are long chains of atomic carbon, oxygen, and hydrogen. These chains consist of identical units linked to each other by chemical bonds. The first stage in making beer involves dipping the grains of barley in water until they sprout. This procedure is called malting. Humidity causes the embryonic cells of the barley to quickly multiply. After a few days, the cells will have produced a host of new chemical compounds. But mostly, they produce enzymes, very large chemical molecules, sometimes consisting of thousands of atoms. Enzymes are biologically active molecules that play an important role in beer making. But they're fragile, especially when kept in a hot and humid medium. To keep the enzymes active, the barley must be kiln-dried. A kiln is a sort of conical oven. This process stops the sprouting and preserves the enzymes. Once a degree of humidity of 4% is reached, the barley becomes malt. The next step is the brewing, which is done in large metal vats. The malt is crushed and mixed with water. In the vats, the mixture's temperature is raised in several precise stages. Under these conditions, the malt enzymes become active. Enzymes are catalysts and are able to identify the molecules of a number of chemical substances and to modify them. The malt enzymes attack the chemical bonds between the basic units of the starch molecules. They cut the starch chains into two families of compounds: fermentative sugars and non-fermentative sugars. The fermentative sugars are small molecules, the commonest of which, maltose, consists of two basic units. The higher the quantity of fermentative sugars, the higher the beer's alcohol content. As for the non-fermentative sugars, they have 4 units or more. They give the beer body. The art of brewing, therefore, lies in balancing the production of fermentative sugars and non-fermentative sugars so as to obtain the taste and degree of alcohol desired. Brewing produces a juice called wort. The chemical reactions that produce the various sugars occur at different temperatures. The brewer can therefore monitor the quality of the wort, which in turn will enormously influence the quality of the beer. After brewing come the filtration and cooking of the wort. Filtration consists of removing the remaining solid malt. The cooking inactivates the enzymes still present in the wort and therefore interrupts the chemical reactions they promote. Moreover, during the cooking, the wort is flavored with hops. Hops contain resins and essential oils that give beer its bitterness. These compounds become soluble in the wort according to the same principle as an infusion. The cooked and flavored wort is then cooled and ready to be fermented. Fermentation takes place in controlled refrigeration vats in which yeasts are added. Yeasts are microscopic organisms, close cousins of fungi. The yeasts attack the fermentative sugars in the wort. They convert them into molecules of alcohol and carbon dioxide. Further, the fermentation generates a myriad of aromatic chemical compounds that will give the beer its fruity flavor. At last, wort has become beer. Once the fermentative sugars have been converted into alcohol, the beer is cooled to stop the fermentation process. A maturing period follows, during which certain undesirable compounds made during the fermentation are eliminated. Carbon dioxide is added to the beer during a last filtration through calcareous rock. This gives it a nice, clear appearance and causes it to froth when poured. To constantly monitor the quality of their beer, today's breweries are equipped with vast control laboratories. Numerous chemical analyses are conducted to appraise such things as alcohol content, degree of bitterness, color, and even the stability of the foam. However, it's the beer lover who will have the final say as to the quality of the finished product. Chemical reactions go on around us all the time. They make engines work, cakes rise, and convert the food we eat into energy. For a long time, we were content to use the natural substances the planet made available to us. Today, we take a more active part. For instance, acetyl salicylic acid, the active agent of aspirin, is no longer extracted from willow bark as it used to be, but is synthesized in a manufacturing plant. A great deal is already known about chemical synthesis, but it's a field that continues to expand. Chemistry reigns supreme in the modern world. Every day, chemical laboratories and plants produce a host of compounds, such as paints, detergents, fertilizers, pesticides, or drugs. All these substances are manufactured by synthesis, a process that uses various means of producing and designing chemical compounds. Today, in efforts to improve its effectiveness, chemical synthesis is the object of a great deal of research. One of the challenges chemists face is synthesizing new organic molecules, or carbon-based molecules. Synthesizing these molecules, which are sometimes highly complex but having countless uses, often requires many steps. Until recently, the only technique available for synthesizing new organic compounds was trial and error. Thanks to computers, today's chemists have an additional tool at their disposal. Indeed, researchers have created a number of computer-aided synthesis programs for organic molecules. The way this software program works is simple. First, the chemist projects the chemical structure of the molecule he wants to synthesize onto the screen graphically. For example, Schηματισμος, a molecule used in the cosmetic industry. The computer translates the structure into its own language. It then builds a synthesis tree, meaning a set of possible reactions that might lead to the synthesis of Schηματισμος. The computer also suggests a series of products from which the molecule might be constructed. To design this program, the computer had to learn hundreds of organic compound synthesizing techniques, each one painstakingly gained through laboratory testing. Thanks to computers, the chemist can try to determine, without leaving his office, the shortest or the least expensive way to synthesize a substance. While some researchers are developing formulas for new chemical compounds, others are working to improve their reaction speed. That explains their interest in catalyzers, among other things. By their mere presence, catalyzers can speed up chemical reactions. For example, a well-known reaction, the conversion of vegetable oil into margarine, happens because of a catalyst. Vegetable oils are made up of atomic carbon chains. Carbon atoms are generally linked to hydrogen atoms and bonded together by chemical bonds. When some of these bonds are double, the oil is said to be unsaturated. Most vegetable oils are unsaturated. However, when hydrogen is added to these unsaturated oils, and in the presence of a catalyst such as palladium, every atom of carbon bonds with a second hydrogen atom. At the same time, some of the double bonds become single. Following the reaction, which would not happen without the catalyst, the unsaturated oil has become an almost totally saturated oil. Saturated oils are usually solid at room temperature. This explains why margarine, which contains a certain amount of saturated oils, is relatively firm. Catalytic techniques are the subject of renewed interest because they are not only the cheapest, but can help combat chemical pollution. For example, chemists are working toward improving catalysts used as anti-pollution devices in car mufflers. As a rule, catalysts are byproducts of precious metals. They promote oxidation and the reduction of pollutants contained in exhaust gases. These pollutants are partially burnt fuel, the carbon monoxide and nitrogen oxides responsible for acid rain. When a catalyst is present, they combine with the oxygen in the air. Therefore, carbon monoxide, a very toxic gas, will, in the presence of catalysts, react with the oxygen in the air. This forms carbon dioxide, a harmless gas, in a reaction called oxidation. Nitrogen oxides are reduced to nitrogen molecules, a natural component of air. This is called reduction. Fuels that are partially consumed in an engine are carcinogenic compounds. Owing to catalytic action, they become oxidized, that is, totally converted into carbon dioxide and steam. Catalysts have another advantage. They are hardly consumed during the chemical reactions they make possible, and thus can be reused. Researchers are looking for ways to improve the effectiveness of engine exhaust catalysts. Indeed, catalytic activity varies according to temperature, and some catalysts only become active when an engine is very hot. Researchers are attempting to develop catalysts that will function in cooler temperatures, which would mean that the pollution emitted by a cold engine would be completely eliminated. It's when an engine is first started that the level of pollution is the highest. They are also trying to improve the lifetime of catalysts. However, to achieve their goal, they must fully understand how catalysts work. This still remains something of a mystery. A Russian chemist, Dmitry Mendeleev, was the first to classify atoms or chemical elements. Today, his periodic table contains 109 elements. The last is called unilenium. Theoretically, we could synthesize heavier and heavier atoms. But if the names they're given are tongue twisters like that one, I'd just as soon never have to present them to you.